Welcome to the fourth and second to last in a series of 5 webinars between ADB and Deltares under the theme Collaborating on Innovative and Sustainable Solutions for Integrated Water Management. And this is brought to you by the Water-Related Risk and Resilience Water Advisory Team by the Asian Development Bank. So let me introduce myself first. My name is Silvia Cardascia, and here at ADB, I work in the Environment, Agriculture and Natural Resources Division in the East Asia Department, and I will be moderating today's webinar. So as you can see from the slide, Deltares are a specialist consultancy working on smart innovation in the field of water and is a knowledge partner of the Dutch government. Deltares covers almost every aspect of water and hydraulic engineering. So together, ADB and Deltares have developed a stimulating series of webinars. And today we have here with us Dr. Albrecht Wertz. He will be presenting on the Yellow River, a hydrological basin approach. So just as a general background for the audience here today, the Yellow River is of great importance and is the second largest river in the PRC after the Yangtze. It's crossing 9 provinces and it's home to around 120 million people. So the basin's water resources are very crucial to sustain people's livelihoods. And in fact, the basin is also considered the food basket of the PRC. It is crucial for agriculture production. In fact, agriculture is one of the largest consumers of water in the basins. It is about 70% of the water usage. The Yellow River is also one of the most hydrologically complex systems in the world, as we will hear today, with tons of sediments flowing downstreams to the basin. Apart from sediment huge load, flood risks and water scarcity are also other big challenges. These are exacerbated by human-driven pollution and climate change issues. ADB is supporting ecological protection and also high-quality development in the Yellow River with a programmatic approach to strengthen institutional coordination and policy reforms for holistic planning, integrated natural resources management, rural vitalization, and agroecological development. So today's presentation is very timely to help water managements, but also other relevant stakeholders here in the room to make informed decisions about reducing risks and impacts of future floods and droughts while maintaining ecological stability in the basin. This is also important for other countries in ADB, so not only for China, countries that are facing, as the PRC, similar water security issues and ecological stress as well. Our colleague here today from Deltares, Albrecht, is an expert on data model integration and hydrological forecasting at Deltares. He investigates on the predictability of the hydrological system, which is driven by weather and climate, to improve predictions of hydrological processes at different spatial and temporal scales. So as of today, Albrecht will present for about 30 minutes. After his presentation, there will be a Q&A moderated by myself and by my colleague in the Sustainable Development and Climate Change Department, Noyuki Mori. So you please feel free to ask questions in the chat box, and these questions will be addressed as much as possible during the Q&A that will follow the presentation. So I guess it's time for Albrecht to present, and so the floor is yours, and thank you very much for participating in today's webinar. Over.
Thank you very much, Sylvia. I hope you can hear me well, so I can start the presentation. Yeah, I will present, I was asked to give a presentation on hydrological basin approach that we use at Deltares, and also highlight some new developments from this approach. First, I start with some information about the Yellow River, although Sylvia already gave a quite good introduction into the issues of the Yellow River basin problems. Of course, when you deal with river basin management and river basin management plans, you have to take into account the changing world and climate. Of course, we have suffered from more and more extremes that can cause all kind of problems along the coast, but also riverbank erosion is a big problem. We deal with floods more and more often. Droughts are more and more occurring and affecting people's life. population increases, causing a lot of pressure on the water demand and water availability. And of course, there's also a population that is growing older in parts of the world. And finally, there's a lot more urbanization ongoing, and also especially in China, this is ongoing. Of course, in the Yellow River, there are huge problems, especially as already mentioned, sediment load, but also water quality is an issue in the lower parts of the middle reaches and the lower parts of the Yellow River. And of course, water resources, the availability of water is problematic, especially due to the water demand from agriculture. And of course, this also causes problems at the lower reach, where these problems accumulate. Present and future issues are, of course, still the reservoirs that are in the basin developed. They have a certain lifetime, so they might need replacement or adjustment. Water quality is a remaining issue for the present, but also for the future. And also the water resources have to be managed well to secure that everybody has drinking water and also the agriculture has water. And this is also crucial for the water quality. In the lower reaches, salt intrusion and saline groundwater also affect the agricultural production, and also this sediment load is causing some issues in the lower reaches and require river maintenance. There are also some possible solutions, of course. You can try to keep the sediment from entering the river by greening the environment. You can smartly operate your reservoirs, smarter. And you can also think about structural measures in the lower reach to deal with the sediment, providing more room for the Yellow River. And in the lower reaches, you can think about nature-based solutions to deal with the sediment issues there. So this is a short introduction into the issues of the Yellow River. I'll move on to if you want to do something about these issues, you might want to make decisions, support decisions that can improve the situations. And what kind of decisions need to be supported? Of course, as I mentioned, you want to mitigate the drought and hazard risks. You want to deal with develop better water management strategies for reservoir management, the sediment management, ensuring environmental flows for a better ecological situation of the river. And also you want to be sure that the things you do make sense, that the investments you will make are not a waste of money. So you want to look into the future and take into account climate change, but also non-climatic drivers as population growth and change in agriculture. So these are the things that you want to support when you want to develop water management and river basin management plans. So what's important in river basin management planning? That it should be evidence-based. This is a water management decision framework, and policymakers need to have a common understanding about the issue, so they have a common data set looking at the same information and have access to the same knowledge, so they can communicate well with each other and make decisions based on the same data. Using global data and rapidly built models can trigger the local expert dialogue on improving these models, improving the applications, and integrate local available data sets that are often not available directly. It also requires an integrated modeling approach. You need many disciplines like hydrology, rainfall-runoff modeling, but also water demand and allocation modeling, water resources, include the water quality issues, water quality modeling, sediment modeling, and also groundwater flow modeling. And finally, if you go to the lower parts of the river, you need hydrodynamic models to deal with the water, simulating of water levels and river morphology. And ideally, you use well-connected models to simulate effects and impacts correctly to support the building of plans and the policy decisions. And ideally, you use the appropriate resolution for these decisions. Of course, you can start with coarse approaches, but sometimes you need to refine these either in space and or time to provide the right decision making. And ideally, you use an approach from global to local and incorporate local data easily within the process. And of course, everybody should have access to the tools. So ideally, they are open or open source. In Deltares, this is encapsulated in a framework that we call BlueEarth, which is basically focusing on stakeholder engagement. And today I will mainly focus on the inner circle of this framework, but I will also go slowly through this framework in the next slides. You start with a stakeholder assessment. Together with the stakeholders, you define the needs. You define scenarios and strategies for the current situation and future situation. You determine what information is needed, what is available, and what can be obtained from either global sources or local sources. And then after that process, you start the modeling framework to be able to understand the current situation in the basin and make plans for the future. And finally, of course, very important is to display this information in an easy dashboard to the stakeholders. And then you go back again basically if you met these stakeholder needs. So this is an ongoing circle, basically. Within the BlueEarth framework, we think about building and running and analyze these models rapidly. We use state-of-the-art data processing methods. It's all built on Python processing. And of course, you want to seamlessly integrate data that is available. And an important component of this BlueEarth is the model builder, which basically is a way to quickly build these models from available data, either globally available or locally provided data. And then this can be integrated into a computational framework, and results can be displayed in a dashboard to stakeholders. Here again, this is a similar display of the idea. We want to support integrated water resources management, engage stakeholders, and basically enable informed and interactive decision making. We make some of the data available that is needed for these rapid building of these models in the BlueEarth data portal. This is still in beta release, and this will grow into the future. But you can take a look if you want. Then if you go to a basin, like for instance, large river basins like the Yellow River, you have a lot of different issues in the basin. So it's very unlikely that you can all do with a single model. So you need, for instance, for the hill slopes, you need rainfall-runoff modeling. In the basin, you have different issues. For instance, you want to build a harbor. You have maybe water quality issues upstream. You have reservoirs somewhere up in the hills, and you have flooding maybe locally in the city. So you need different kind of models to support this. So rainfall runoff for the steeper areas, groundwater flow modeling in the lower parts, also river flow hydrodynamic modeling in the lower parts, and reservoir management. And that depends a little bit on what kind of decisions you want to support. If it's more real time, maybe you want to focus on real-time control applications, but otherwise more simplistic reservoir management models can be used. And then finally, you try to model this all in an integrated manner and connect it to each other. So as I said, part of the crucial part of this BlueEarth data modeling framework is the HydroMT, the model builder, where we basically build based on global data, high resolution local models. And we make use of all sorts of available global data, for instance, the Merit digital elevation model of Dai Yamazaki, which basically provides the digital elevation model to derive hydrological models and the river network. We use OpenStreetMaps, for instance, but also data from space or local data or data from GEPCO for coastal models. And also data available from satellites to basically obtain reservoir areas, as you see in the bottom right, are integrated into this modeling framework. We make use of other high-resolution global data sources, especially for rainfall runoff modeling and recharge modeling. We use soil grids and also the land use data from FITO, or glob cover, or for instance in Europe, Korean. The hydro and the Merit data, the digital elevation model, is being used as a baseline for all these kind of models. We pre-process these elevation data into river networks and all sorts of other subgrid related data, such as slope, up area, and these types of things. And these provide input data for the rainfall runoff model, but also the groundwater model where the river is flowing, and can also be used for the hydrodynamic model and the water quality model to derive these automatically. Then we use this derived river network in a scalable high resolution model, which we then tested, for instance, for the Rhine River, which was published recently. And we use, for instance, the soil grids data to derive a lot of these parameters from the hydrological model at the highest resolution, so at 250 meters, and then use upscale rules to derive the model at coarser resolutions, for instance, 1 kilometer or 2 kilometer, without the need to recalibrate these models. Of course, there are some parameters that cannot be derived from these global data, so they might require minimal calibration. We also do the same thing with groundwater flow modeling. This is an example where we apply these tools to derive a global groundwater model at 1 kilometer. This is ongoing work by Jarno Verkijk from our soil and groundwater department. And these models can also be derived at local scales for local river basins, as I show in the next example. Provide an example of the Ganga River, which is the mostly densely populated river basin in the world. A huge population of 700 million people, covering a couple of countries and a very big area, and also includes high mountains and flatter areas near the coast. And also in the Ganga River basin, there's a huge water demand from agriculture, and it's also highly polluted. The objective of this study was to strengthen the capacity with respect to strategic basin planning, and also develop a set of scenarios and strategies for the Ganga basin, and then also provide a strong and accessible knowledge base, both in data but also tools. And then, and the most important, of course, establish a multi-stakeholder engagement process to support strategic basic planning. And this project was carried out over the period 2015-2018 together with ACOM and Future Water by Deltares. We used the model setup as I just described, integrated tools using the same base data and connected and integrating local data. We used the ModFlow model for the groundwater model, the water quality model derived from the derived river network, and for the rainfall runoff recharge we used WFlow hydrological model, and then connected this to a RIBASIM model for river basin simulations. If we look at the workflow in more detail, it looks like this. It's, climate scenarios provide input forcing for the hydrological models. The hydrological models provide the input for the groundwater model and for the river basin simulations to basically deal with water use and distributions. And then these simulations were used to derive water quality measurements, water quality models to say something about water quality. And also future water use and management scenarios were connected to the rebasin model. And finally, this data was made available to the stakeholders in the dashboard. The scenario and strategy assessment was done with the stakeholders to see what scenarios were likely and what kind of strategies should be assessed. And then finally, this information was made available in easily accessible web dashboards that were available to the stakeholders. Some ongoing developments related to the modeling. As I said, the W flow model, as I showed before, a grid-based model, can also be used for flood forecasting. This is an example where we set it up for the high river basin, basically next to the Yellow River Basin, and set it up at the 1 kilometer scale, using the same open source data, and then couple this with meteorological forecasts from a local party in China. And we also use the same setup to basically support streamflow forecasting in Taolinkou at high resolution. And this is a multifunctional reservoir, which is important for water supply, flood control, and hydropower. And as I said, this also here, the distributed model takes advantage of the open data, but of course, information about rainfall and also the measurement data from rain gauge or from the hydro stations are important to say something about the quality of the model. And as you can see, this is a very relatively dry area, and then suddenly you get high peak flows. Using the same data, using the same setup, we can set up very quickly water quality models with the hydrological model providing the flow information. This is an example for the Rhine River in the Netherlands and Germany and Belgium. This is the Meuse and the Rhine. And this work is conducted for the CHR, which is the Hydrology Commission for the Rhine, where we look at water demand scenarios and their effect on water quality. And here, what is displayed is an indicator where we translate water quality concentrations to a toxicity indicator, which was developed in the Solutions project by Deltares. We can also do this at an even larger scale. This is related to the ongoing UN Global Water Quality Assessment, where we start doing these types of simulations at continental scales. Of course, we have to be aware that the results of these kind of models doesn't make sense everywhere in Africa. But validation is ongoing. We can also use these hydrological models, which are gridded and available at high resolution, to basically calculate how much soil is lost and how much sediment enters the river. And this is, for instance, an example where we use these kind of approaches to calculate the soil losses in the Seine River Basin, and then also using two different approaches and then validate it with data from the literature. And then this can be input for a hydrodynamic model to calculate basic river morphology and all sorts of issues within the river basin downstream. Another important aspect of river basin management modeling is the data for water use, which is often available only on very coarse resolution. But if we want to go to higher resolution modeling, which we think is important for more locally relevant decision making. We also have to develop approaches to come up with water use demand, water demand data at high resolution. And in a research project like the H2020 European Climate Prediction Project, we are trying to develop smarter ways to derive sectoral water use at high resolution. And this is conducted with the Utrecht University. And we make use of population data at high resolution and also land use data sets. And that can, of course, vary locally. In Europe, we use Korean, but maybe in China, we could use the phyto data set. Conclusions: water resources, reservoir management, water quality, sediment problems in the Yellow River system need to be considered together. And then for this policy-informed decision-making, you want to do this evidence-based, sharing the information with stakeholders, make sure they have the same access to the same information, access to the same knowledge. And ideally, you combine global and the local data. We support an integrated modeling approach, rainfall runoff, groundwater, water demand, water resources, reservoir management, water quality, and river hydromorphodynamics. And yeah, we use more and more flexible approach where you can set up these models rapidly at different resolutions using open or open source tools. And this also is important in the interaction with the stakeholders, because you can, if it's flexible and rapid, you can also make changes to this setup quite easily. And last but not least, these kind of models can also be used in operational water management instead of only being used for policy. For operational forecasting, I showed one example for China. And then you can either use the integrated link models in a similar setup. Of course, you need a more tailored data management system, for instance, in Delfuse. And if you look at reservoirs in real time, you might want to use more fancy approaches for real-time control of those reservoirs. And I think the next talk by Nadine Slowikis will go into more detail about operational forecasting. One thing I like to highlight is also the term digital twins. That is also for monitoring, understanding, and stakeholder dialogue. If you have these models derived for river basin management planning, you can also use these models in a digital twin, and then have an ongoing, continuous interaction with stakeholders about the river system you are interested in. Okay, this was basically my presentation. Thank you very much. If you have questions, let me know.
Thank you very much, Albrecht, for the very interesting presentation. And I guess we have already some questions in the chat box. I guess it's a very interesting approach because it looks at all the different aspects and it is integrated. So it integrates models, but also I think one of the most interesting things is the integration of stakeholder and decision making into the process and the models. I'm just reading through the chat box to pick some of the questions. One relates to, I guess, what you presented on India. So a question is, which institutions in India is handling the Ganga River Basin model? So maybe we can start with this one, and then we can pick other questions forward in the chat box.
Yeah, I think there were many institutions involved: National Institute of Hydrology, what is it called? The Commission of I cannot recall the name, but there were many institutions many stakeholders involved in the whole Ganga project. There was not only one; there were many.
Okay, so
I can elaborate on that later. It may be also in written form if needed.
Okay. A second question was related to, so how does the water demand model work? What is the basis of making projections of demand? And perhaps I can also add a second question because I think it's related. Can you share an example of a dashboard with the audience?
The water demand is often, as we want to go to high resolution, often related to population growth, but also economic scenarios related to economic developments. And also you have institutes that project land use changes into the future. And we can combine those type of information to develop water demand scenarios and then use that as input or boundary condition for the modeling. The dashboard, I don't have an example here on my computer, but of course we can make links available to dashboards that were developed for these kind of things. Okay,
and perhaps this can be shared later with your presentation as well. Another question we have is if these models require an instrumentation to be set up in the river basin.
Can you repeat that?
Instrumentation, I guess, tools or...
No, the idea is that these models are being created in an automatic fashion, but using these global data sets that are available to everybody. And then these models can, these are often, like ModFlow is open source, the WFlow framework is open source. So these models are freely available to stakeholders, and they can run these models on their own computer. These can be run by other people if needed. But the data is available from global data sources. The algorithms that we develop are either open or open source as well to derive these parameters. So in that sense, it's highly flexible and accessible to stakeholders. Does that answer the question? Because I don't see the question, so.
I hope so, but we will see if there are follow-up questions. I just move ahead because we have many in the chat box. Another one relates more on the water demand allocation and priorities, and it's a sort of double question. The first one being, does the model include information about the legal status of various demands? And the second part of the question is, can alternative demand priority scenarios be modeled? And is this part of the exercise?
Yeah, that is something you develop with the stakeholders, so you can include that in the RIBA-Sim model. You can include those types of things, priorities in the planning and in the model. So yes, I would say yes.
Okay. How this model is synchronized with other variables like land use and land changes in different parts of the river basin? Well, I guess this is
land use is included to derive lots of parameters for the hydrological model setup for the rainfall-runoff model. And of course, if land use changes, then you have to rederive these models. So you could basically make these parameters dynamic with the simulation to take into account these land use changes. So these things are included in the model setup. Land use is linked to, for instance, the depths of the routing depths. The LAI is included. So if these things change, you can take that into account in the framework by making these dynamic parameters. Like models like the ModFlow, they are more static because the hydraulic properties of the deeper layers of the soil, they are not so changing so frequently, not so rapidly. So for the rainfall runoff part, you can make this more dynamic.
I hope it answered the questions. Could you please explain about the limitation when using BlueTech modeling system?
The BlueEarth modeling, yeah, in principle, there's, of course, we'll try to model phenomena at the right resolution and the right, both spatially and temporally. Of course, the limitations are the quality of the base data layers, these global data sets. They are not good everywhere in all places across the world. So there are limitations in these data layers. And of course, a very important limitation is the quality of the forcing data, which is also varying globally. So if you do projects, for instance, in Europe, the quality of this forcing data, rainfall data, temperature, and potential evapotranspiration data is very good. But in other places, for instance, like in Africa, the quality of this data is not so good. So this will affect, of course, a lot the outcomes of your model. So the quality of the forcing data, which is a very important aspect, and often it is needed to include local data, local rain gauge data, information. This was, for instance, also in India. This was one of the things that came from the Indian Met Service. They provided the best forcing data, and then we integrated it with the globally available data sources. So these, often the forcing is one of the biggest limitations, and also the quality of these base data layers, like SolGrid, is not good everywhere, and also these land use maps that we use are not. The quality is not always perfect everywhere. So.
Mm-hmm. Yeah, and I guess this goes back also to the stakeholder engagement and the types of agencies that participate in data, in providing data, because of course in emerging or developing countries it's more difficult to have good quality data, but if agencies provide, then of course this can help. I think the second part of the question related to if there are any training to learn about this model. Not that I know about ADB, but perhaps, I don't know if you have any free training online on Deltares available for people who want to play.
There is training available online, and often also, of course, also in these types of projects, this not only stakeholder engagement, but there's often, of course, always also a lot of training related to train stakeholders to use these tools for their own specific basin. But there are courses, there is course material online, and of course you can also, there are dedicated courses where you have to provide a small fee to cover for the person's cost that gives the training. But I think there's a lot of material online available, and I can provide links if needed.
Okay, thank you. How do you select scenarios for evidence-based decision-making?
And that is something you do with the stakeholders. This is not something you can do by yourself. So what kind of scenarios are plausible, and these are typical things that are part of the stakeholder engagement process, where there's a lot of input from the stakeholders, what they think is realistic. And the evidence-based is more that you provide the same information to everybody, and everybody has access to the same knowledge, so they can make decisions based on the same data. But the scenario planning, this comes from often input from the stakeholders.
Mm-hmm. And stakeholder, I guess they're also then involved in the future planning. So after identifying the gaps and the planning issues, then stakeholders are then engaged in a second phase process.
Exactly. So this is continuous, yes.
Okay, then we have a question by the Department of Health in the Philippines. And it is about how do you address El Nino and La Nina phenomena and the effects of climate change into your model?
So yeah, the model setup is basically hydrological model linked to other models like groundwater, water quality, etc. So the forcing data is the data that drives these models. So we start often with assessing the current situation using available measured meteorological data, gridded form or in available as gauges. Then of course we have to interpolate the data, but the current situation is then based on observed data or from reanalysis data like the ERA5 data set. And of course you also have locally data sets available, reanalysis data available. And then for future runs, we make use of climate scenarios, for instance, from CMIP5, CMIP6. These are also becoming more and more available at high resolution. So we use these climate data to then develop outlooks for the future. And then that is the input for these models, and then you can see what happens to either the water quality or the water resources, and then you can play with different scenarios. If you change something in the agricultural side of things, then how does this impact the availability of water and the water quality, for instance? So the data coming, the forcing data is either observed meteorological data in a gridded form, and then we use climate scenarios for the future, with or without bias correction.
I hope that answered the question. The next one we have is, what is the ideal size or scale of river basin for using the model?
I like to stress that it's not, I hope this was clear from my presentation, that it's not one model, it's a series of linked models, and the scale can vary. But for instance, the whole river, the whole Ganga project was conducted at a kilometer scale to account for all sorts of local interaction of land use and climate. And then the river basin simulations, that is on where we basically provide the input data to the river, etc. That is a river network, so that is a network model. So this is, and that is also was operated at a monthly time scale. So it depends very much on the questions that people have. We do the water balance calculations at, for instance, daily or sub-daily at high resolution, and then this provides input to a river basin management simulation model like RibaSim, where you basically can calculate either on daily but also on monthly scale. Depends a little bit on what kind of management decisions you want to support, but also, of course, what time is available to come up with an answer.
Okay. So the second one, I guess it's a follow-up question on the data one. So there are many integrated models, all with their range of errors. Did you compare simulations with real-world events? And how well do the simulations compare to measured data from best case to worst case? And what options do you have to compensate for lack of data?
Yeah, good question. Of course, as I said, the quality of these modeling efforts depend a lot of the forcing data. So that, as I said, this is not constant everywhere, but we have good. We obtain good performance in various parts of the world using this model setup. For the Rainfall-Runoff model, we are testing this in every continent, and depends a little bit on where you are. You get better or worse results. But often this is related to the input data. And for the groundwater modeling, I mean, there are lots of publications available where it's shown how good these models can operate, but this often depends very much also on the forcing data that is available. So it's very difficult to give a general statement. It's this big or this large. It depends on the place in the world you are, yeah, the quality of the underlying data sources, and the available data for the forcing, as I already mentioned. But in many places of the world, we get quite good results using these model setups. And sometimes it's not even the most important to get the perfect answer. It's also to look at relative changes. Of course, you have to have a certain trust in the model, the modeling, the linked model setup. But you can look at relative changes from current situation to future situations, especially also because these climate scenarios, they also have a certain bias, and you cannot always account for those biases. So you look at relative changes if you look into the future instead of absolute changes.
Have an estimate. So for river basins elsewhere in the world are confronted with huge sedimentation problems. Does Deltares have some solutions in some selected river basin?
Good question. I'm not sure that I'm the perfect person to answer this because I am not the river morphology person, but I can maybe provide written answers to that question. Of course, we have solutions, but if they work everywhere, that is of course debatable.
Next one is linking these models problematic? For instance, different time steps, different response times, two-way feedback linkage, stability issues, etc.
This is also part of the ongoing development. It's quite technical, so I didn't include it in the presentation, but we are working on, of course, sequential coupling is not so difficult. It is actually quite straightforward. The two-way coupling, that's more a technical issue where we work on, where we couple two-way, for instance, the rainfall-runoff model to the mud-flow groundwater model using the basic model. This is a technical term. This is the basic model interface, which is basically a global standard of how you can couple models with each other on a time-stepping basis. And of course, there are also examples in the scientific literature where we already did these types of things, where we coupled, for instance, a hydraulic model to a groundwater model using this basic model interface. So if needed, I can provide some links to illustrate this. But this is also ongoing work.
Okay, so perhaps we can provide all the links
Yes.
to the different documents that people were asking in a follow-up email. Another question is how effective this model would help to plan holistically river linkages and judicious use of equitable water availability across India. The Eastern India is having excess water availability, whereas the western part is generally devoid of it. And that's the query.
I find it difficult to answer this. It's not like an easily question that you can answer easily, and I'm not sure I'm the right person to answer that question. So maybe I can also do this in a written form later on to this question.
Okay, so there are no more questions from the chat box. I actually had a curiosity because this presentation is about the Yellow River, and I just wanted to know what is the level of development already of the model in the Yellow River, and how do you plan to take it forward? What are the agencies that you're working with, and what are the several steps that you're planning to develop the model further?
If I go back to the slides, for instance, these are like projects we do in the region, of course not in the Yellow River Basin, but next to it, where we work with Chinese partners to develop these models. And for the Yellow River, I mean, these models, as I said, they can be set up basically on the fly, and then with the appropriate organizations locally be further explored. So it's the idea is that you not depending on the question, these models can be set up at different temporal or horizontal spatial resolutions, and with the local partner that has an interest, this can be worked out in more detail. Does that answer your question?
Yeah, but are you do you have already set up sort of like stakeholder or institutional engagements of different agencies, or you just
yeah, I think with the Yellow River Basin Commission there are contacts, certainly.
Okay, good. So there are no more questions in the chat box. I don't know if your questions, I'm speaking to the audience here, if any of your questions have not been answered, and if not, this is the time to ask for follow-up questions. We still have 5 minutes to go, so we still have some minutes to ask if you have burning issues to Albrecht. Well, if not, I would ask Albrecht if you have any closing remarks or any things that you want to say to ADB or the larger audience, or in terms of even follow up, if you want to leave your email address or something that people can follow up with you directly or through the Sector group. Or
no, it's not at the end of the presentation. So people can contact me directly via this email address. And I'd like to thank everybody for attending this presentation. I hope it sheds some light on approaches developed at Deltares regarding river basin management planning and stakeholder engagement, which is an important part of this process. So, thank you very much.
Yeah, we actually have one last minute question, which is the stakeholder engagement follows an iterative process. I assume when are these made, and don't they limit the scenarios?
Excuse me, the last part I didn't hear.
When are these made? I guess Jelle, do you want to reformulate your question? Perhaps it is not clear to me as well. So the stakeholder engagement follows an iterative process. When are these made, and don't they limit the scenarios?
I mean, you start with an inception phase. You have contacts with these stakeholders continuously, and then if there's new information that can be shared, you can you basically have a series of workshops and get-togethers to discuss results, and then you can fine-tune again and see what is realistic or not together with the stakeholders, because they have to make the decisions and they decide what is realistic or not.
Mm-hmm. And so it's a step-by-step process.
Yeah, and back and forth.
How many workshops do you normally have? Do you have planned for this sort of assessment?
That often, of course, also depends on available budgets, but
yeah.
No, I cannot say one figure, but many. So.
Mm-hmm.
And for instance, in the project for the Ganga, there was somebody from Deltares in Delhi for the whole period of the project. So.
Okay, so yeah, it also depends probably on the magnitude, on the dimension of the basin, and
yes.
the number of stakeholders involved.
Yes.
Okay. So this is a reminder from ADB Water Sector Group from the organizers. So you can, this is a reminder for everybody that you can find the slides on the SharePoint link that was shared on the chat box. And if not, you can drop us an email and we will share the presentation with you. Okay, so I guess if there are no more burning questions, I'll just close the session and say a big thank you to Albrecht and Deltares for this very informative webinar. And I guess the last one will be the fifth and last one to be held, I guess, at the end of September or in a couple of weeks' time. So we will keep you informed. Okay, so the next session is 6th of October. So we will have another webinar with Deltares, and that will be the last one in the series. So we hope you enjoyed, and stay tuned for the last webinar. Thank you very much.
Thank you.